Hello friends, IBM is here with another episode of Learning Physics, and do not forget to subscribe to this channel. Don't forget to download the document. Download the document in the video description so that you can have a printed copy so that following the questions is very easy in a hard copy format. Note that this is actually oscillations and simple harmonic motion. Oscillations and simple harmonic motion. I think this is part 3 of these sort of the past paper questions. Note that along the way in these videos of oscillations and simple harmonic motion, we are supposed to discuss questions relating to the types of oscillations, the meaning of simple harmonic motion, and bodies which are performing simple harmonic motion, forced and damped oscillations, energy of oscillations. We shall see, we have been seeing graphs in part 1 and part 2, and we shall be seeing graphs, questions relating to resonance, and many more. So without wasting any time, let's go to our past paper questions. That is the document. If you have already downloaded it, then it is very good. If you haven't, consider downloading it. You can print per topic so that you follow the topic as discussed in the videos. This is the last topic in paper 4, Cambridge Physics 9702. So let's go direct to our past paper document. I think in the previous video, in part 2, we stopped on page 348, and I want us to start from there. This will be a little bit longer because I have enough time today. It could be 3 hours. So let's start. A student sets up the apparatus as illustrated in the figure in order to investigate the oscillations of a metal cube suspended on a spring, as we see here. The amplitude of the vibrations produced by the oscillator is constant. Amplitude is constant, that is the maximum displacement. The variation with the frequency of the amplitude of the oscillations of the metal cube is shown here. So this is the variation of amplitude with the frequency. So state the phenomenon illustrated in the figure here. Of course, the phenomenon, this is resonance. We have already seen such a graph. This is what we call resonance. When maximum amplitude occurs at a certain frequency, which is equal to the natural frequency, then resonance has occurred. The system absorbs maximum energy and vibrates with the maximum amplitude. For the maximum amplitude of vibration, state the magnitudes of the amplitude and the frequency. So for maximum amplitude of vibration, we just look at our graph to find the amplitude. So this is the maximum display, the maximum amplitude. And the scale on the x-axis, I think it is 5 divided by 10, which is 0.5. So this is going to be 16. So each small box is 0.5, so the amplitude is going to be 16 millimeters. Then the frequency for maximum amplitude of vibration, state the magnitudes of amplitude and frequency. So the frequency at which maximum amplitude is occurring, I think this is the point, and this frequency is this value here. The scale here is 4 minus 2, that is 2 divided by 10, that is 0.2. So the frequency here is 4.2, 4.4, 4.6. So the frequency is, this point here is 4.6. So the frequency is 4.6 Hertz. The oscillations of the metal cube of mass 150 grams may be assumed to be simple harmonic. Use your answers in A Roman 2 to determine for the metal cube its maximum acceleration. From the defining equation of simple harmonic motion, we know that acceleration is equal to negative omega squared x. Acceleration is directly proportional to displacement, which means it is going to be maximum when the displacement is maximum. Remember, angular velocity or angular frequency is equal to pi times f. So we are now substituting. I will ignore the negative in further calculations. So the maximum acceleration is going to be equal to omega, which is 2 pi f, and this is squared times x naught, where x naught is going to be the maximum displacement. So this is going to be 2 pi times f. We have obtained f as 4.6. So this will be 4.6, and this will be squared. Then times the maximum this amplitude, we got it as 16 millimeters. So this will be 16 times 10 power negative 3. I'll just check this on my calculator. So from my calculator, this is 13.4 meters per second squared. The maximum resultant force on the cube, maximum resultant force. So we know that force is mass times acceleration. Of course, if acceleration is maximum, then the force is also maximum. So the maximum resultant force is going to be equal, the mass was given as 150. So that is 150 times 10 power negative 3 to change it to kilograms, times the maximum acceleration, which is 13.4. And I will check my calculator, times 150. So from my calculator, this is to two significant figures, 2.0 newtons. Some light feathers are attached to the top surface of the cube, so that the feathers extend outwards beyond the vertical sides of the cube. So what is happening? Straight away when you see feathers being added, it means air resistance is being added, so we have what we call damping. The damping has been increased. The investigation is now repeated. Draw a line to show the new variation with the frequency of the variation of frequencies between 2 Hz to 10 Hz. So damping has been increased by attaching feathers on the cube, so that air resistance is increased. So what does that mean? If air resistance is increased, it means the maximum amplitude of vibration for the same range of frequencies decreases. Secondly, because damping has been increased, actually the natural frequency of vibration of this system has been lowered, so it means the resonant frequency is also going to be lower. What does that mean? A new graph is going to be drawn whose peak is to the right, to the left of 4.6, because it is now maximum amplitude is now going to occur at a lower frequency. So the peak is going to be slightly less at a frequency less than 4.6, and the line is going to be below the one that we already have. So I will sketch this. So I'll make sure that my frequency, my peak is somewhere there. Okay, so this is going to be my new graph. This is going to be my new graph. First of all, it is below the first one. Secondly, the peak, the maximum frequency is slightly to the left of 4.6 Hz. And it's also going to be a little bit more flatter. It's a little bit more flatter than the one which is already there. So that is the new shape of my graph. I think I'm worsening it again by drawing a second shape. Okay. A bar magnet is suspended from the free end of a helical spring as shown in the figure here. So we say magnet, one of its poles is in the coil. Of course, when this switch is opened, the magnet will oscillate freely with its natural frequency. One pole of the magnet is situated in a coil of wire. The coil is connected in series with a switch and a resistor. The switch is open. The magnet is displaced vertically and then released. As the magnet passes through its rest position, a timer is started. The variation with the time t of the vertical displacement y of the magnet from rest position is shown here. So when the switch is opened, of course, we see that the amplitude is constant. It is constant up to around that value of time. Then it's constant actually up to around this time, 4 seconds. At time t equals 4 seconds, the switch is closed. And what is the effect of closing the switch? We see that now the amplitude is decreasing exponentially. The amplitude is decreasing exponentially after 4 seconds. State the evidence for the magnet to be undergoing free oscillations during t equals to 0 to t equals to 4.0 seconds. So between t equals to 0 to t equals to 4.0 seconds, you notice that the amplitude remained constant. That means no energy is gained or lost to the surrounding. And if that is true, then the system is undergoing free oscillations. So here, the amplitude remains constant. Because the amplitude has remained constant between t equals to 0 to t equals to 4, then we can agree that actually the system is undergoing free oscillations. No energy is lost or gained from the surrounding. State with a reason whether the damping after t equals 4 seconds is light, critical, or heavy. Of course, this damping is light, as you see from the graph. You see that the gradient, the amplitude is gradually or exponentially decreasing. An exponential decrease with oscillations as seen represents light damping. If it was critical, you wouldn't see oscillations. If it was heavy, you wouldn't see cycles. You just see the system just gradually goes to equilibrium without any oscillations. But here we see there are still oscillations. You can see cycles, but their amplitudes are decreasing. So that's what we call light damping. So we say amplitude decreases gradually. Amplitude of oscillation decreases gradually or slowly. So this is light damping. So that is light damping. Okay. Then determine the natural frequency of vibration of the magnet on the spring. Natural frequency. So we know that frequency is equal to 1 over the period. So we just need to look for the period from the graph. Let's check the period. Period is the time for one cycle. So I can start from t equals to 0. One cycle stops here exactly. And these are 1, 2, 3, 4, 4 small squares. Each small square is 1 divided by 5, that is 0.2, I think, times 4 small squares to make one cycle. This is one cycle. There are 4 small squares making up one cycle, but each small square is 0.2. So it means the period is 0.8. So the period is going to be 1 over 0.8 in seconds, or 80. Then I press my calculator. 1 divided by 0.8. So the frequency is 1.25. Explain why after time t equals to 4 seconds, the amplitude of vibration of the magnet is seen to decrease. After t equals 4 seconds, the amplitude of vibration is seen to decrease. We have already seen that it is light damping. Remember initially, before t seconds, the switch was open. This switch was open. And if that switch was open, when the magnet was oscillating, we can't say there was an induced EMF because there was an incomplete circuit. But after 4 seconds, when the switch was closed, then there is now a complete circuit. So that means now when the coil of wire cut the magnetic field, an EMF is going to be induced. Energy is going to be dissipated in this resistor because the current is now flowing. And if energy is dissipated in the resistor, that energy is coming from the oscillations of the magnet. So it means the magnet must be losing some of its oscillatory energy or energy for oscillations as thermal energy is dissipated in the resistor. So the current which is generated or induced in the coil causes thermal energy to be dissipated in this resistor, and that energy is being derived from the energy of oscillations of the magnet. So we expect the oscillations to die out with the time because there is loss of energy to thermal energy which is dissipated in the resistor. So we can simply say as the magnet moves in the coil, as the magnet moves in the coil, a current is induced in the coil. A current is induced in the coil. That is in accordance to Faraday's law because the coil cuts the magnetic field. So in accordance to Faraday's law, a current is induced in the coil. The current in the resistor gives rise to the heating effect. So the current in the resistor, because that current will now flow through the resistor. The current in the resistor gives rise to a heating effect. Or power is dissipated in that resistor, and this heating effect or the thermal energy is being derived from the energy of the oscillations. So this thermal energy, which is the heating effect, this thermal energy is derived from the energy of oscillation of the magnet. So this thermal energy is derived from the energy of oscillations of the magnet. This is not the spelling of magnet. So because some of the energy of oscillation of the magnet is being converted into thermal energy in the resistor, then the oscillations are basically going to die out. Because remember, energy is directly proportional to amplitude squared. So as energy is being wasted as heat in the resistor, the amplitude of oscillation goes on reducing. A horizontal plate is vibrating vertically as shown in the figure here. So we have the plate is vibrating up and down, and there is a cube of 5.80 grams resting on the plate. Calculate for the cube the energy of oscillations. Of course, the energy of oscillations of the cube must be the same as the energy of oscillation of the plate, because the frequency of the cube is the same as the frequency of the plate. So energy, since we want just energy, then that is total energy. So energy of oscillations is equal to a half m omega squared x naught squared. Remember, omega is 2 pi f. And if that is true, this is going to be a half times the mass. The mass is 5.8 times 10 power negative 3 times, oh, by the way, this, okay, times omega. Omega is 2 pi f. So this is 2 pi times the frequency, which is 4.5, and this should be squared. Then times x naught. X is the amplitude, which is 3 millimeters. So that would be 3 times 10 power negative 3, and that is squared. So we press our calculator here. So this is 2.1 times 10 power negative 5. So the energy of oscillation is 2.1 times 10 power negative 5. Do not write any answer which is not exact to less than two significant figures. The amplitude of oscillation of the plate is in B is gradually increased. The frequency remains constant. At one particular point, the cube just loses contact momentarily with the plate. State the position of the plate in its oscillation at the point when the cube loses contact. State the position of the plate in its oscillation at the point when the cube loses contact. Of course, if the amplitude of oscillation is increased, it means, of course, the cube they are vibrating up and down. When it goes down, of course, the cube may not easily lose contact when the metal plate is moving down. But when it moves upwards, there could be a point at maximum height where the cube gets a smaller projection by the metal plate at the highest point. When the metal plate becomes stationary, the cube may continue slightly with with the speed it has gained from the metal plate. So that means the position of the plate in which its oscillations, the position of the plate in its oscillations at when the cube loses contact is most likely going to be when it is at maximum displacement above the equilibrium position, not below the equilibrium position. So this is going to be at maximum displacement above rest position. At maximum displacement above the rest position. So the cube will lose contact at maximum displacement above its rest position. What do I mean? If this is the equilibrium position, when the plate is here, the cube, when the plate reaches the highest point in the process of starting to move downwards, there's a possibility of the cube to continue to retain. There's a possibility of the cube to retain the speed which it has obtained from the moving plate momentarily before it now returns to fall downwards. So that is at maximum displacement above the rest position. Part 2, calculate this amplitude of oscillation. Calculate this amplitude of oscillation. So you can find that amplitude of oscillation So when the cube just momentarily loses contact with the metal plate, what is happening? The cube is no longer going to be moving with the acceleration of the plate. It will now be under the influence on the gravity at that particular instant. Therefore, if acceleration is equal to negative omega squared x naught, of course at maximum height this will be at the highest amplitude. When it just loses contact, then it means acceleration of the cube is going to be the acceleration due to gravity, which is 9.81. At that instant, when it just loses contact, the acceleration will be the acceleration due to gravity, which is 9.81. So 9.81 is going to be equal to, the angular frequency was 2 pi times f, which f was 4.5. Then this is going to be squared, then times that maximum amplitude x naught. So when I press my calculator, 9.81 divided by 2 pi times 4.5 squared. So this is 1.2, 1.22 times 10 power negative 2 in meters. So that is x naught, or the amplitude of oscillation. A small frictionless trolley is attached to a fixed point A by means of a spring. A second spring is used to attach the trolley to a variable frequency oscillator as shown in the figure. Both springs remain extended within the limit of proportionality. In other words, Hooke's law is still obeyed. Initially, the oscillator is switched off. That means there are no forced oscillations. It is just free oscillations. The trolley is displaced horizontally along the line joining the two springs and is then released. The variation with the time t of the velocity v of the trolley is shown in the figure here. So this is a graph of v against t. Use the figure to state two different times at which the displacement of the trolley is zero. Displacement, velocity, remember velocity is maximum when displacement is zero. Remember v is equal to omega square root of x naught minus x, these are squared. When x equals to 0, v is equal to omega times x naught. Because this is 0, you get the square root to remain with this, and this is the maximum velocity. So this velocity is maximum when displacement is 0. So on the graph, when you see maximum velocity, you just know at those points the displacement is 0. So the question is telling us to state two different times at which the displacement of the trolley is 0. So you can start with 0. I think this is 0 0.1, 0 0.3, 0 0.5, 0 0.7, 0.9, 1.1, all those values of time. So we have 0 0.1, 0 0.3, 0 0.5, 0 0.7, 0 0.9, and 1.1. All those values of time, you just choose two of these values. Okay, then the acceleration in one direction is maximum. Acceleration in one direction, that is in the same direction. Remember, this is a graph of velocity against time. Acceleration is the gradient, and you notice that the gradient is maximum when the line is crossing the x-axis. This one is a negative gradient, a negative gradient, a negative gradient. And at 4 it is a positive gradient, at 8 is a positive gradient. So they want in one direction. So I can choose 0 0.2, 0 0.6, or 0 0.2, 1.0, 0 0.6, 1.0, and so on and so forth. That is in one direction. By the way, I could also choose I could also choose this 0, 0.4, 0.8, and so on and so forth. So the acceleration in one direction is maximum. So I have said you have choices such as you could choose 0 and 0.4, or you choose 0.4 and 0.8, and so on and so forth. That is if you choose a positive gradient. Alternatively, you can choose a negative. These ones were positive. You can choose for negative gradient. We have 0.2 and 0.6. That is, or you choose 0.2 and 1.0. Or you choose 0.6, 0.6? Yes. You can choose 0.6 and 1.0. These ones give us these ones are for the negative gradient of the graph. So there the acceleration is maximum. Note that the acceleration is maximum when the velocity is 0. The acceleration is maximum when the velocity is 0. And of course, we know that the velocity is maximum when the acceleration is 0. Okay, so here I have just chosen 0 and 0.4. You could choose 0.4 and 1.0. Those are positive gradients. No, 0.4 and, did I say 0.4? I want positive gradients, 0 and 0.4. 0.4 and 0.8, yes. 0.8 and 1.2. You can also predict 1.2. 1.2 can also work here. So you just need a pair of these two, 1.2. These ones are positive gradients and these ones are negative gradients. Then when they say in opposite directions, then it means you will choose one here and one there. That is in the opposite directions. Acceleration maximum, but in opposite directions. You choose one from the positive gradients and one from the negative gradients. But since they wanted only one direction, then you choose from the same nature, from the same sign of gradient. Determine the frequency of oscillation of the trolley. We want the frequency, so we need a period. Frequency is going to be 1 over period. So we just look for the period from the graph. And you notice from the graph that the period is 0.4. So just substitute 1 over 0.4. I think 1 over 0.4 is 2.5 without even pressing the calculator. Then the variation with the time t of the displacement of the trolley is sinusoidal. The variation with time of the velocity of the trolley is also sinusoidal. State the phase difference between the displacement and velocity. State the phase difference between the displacement and the velocity. Of course, if the displacement is x equals to, let's say, x naught sine omega t, then the velocity is going to be the derivative of this, which will be negative omega x naught cos omega t. So this one implies that actually one is ahead of the other by a quarter a cycle. So the displacement is going to be 90 degrees, or it is going to be a half pi radians. So the velocity time, the variation of displacement with the time and velocity with the time are actually 90 degrees out of phase. So that is 90 degrees, or it is a half of pi. You can verify that. Alternatively, you can look at it like this. Velocity is maximum when displacement is 0. That is a quarter cycle apart. Velocity is maximum when displacement is zero. Displacement is maximum when velocity is zero. So that means they are 180 they are 90 degrees apart. The graphs will be 90 degrees out of phase, or a half pi radians. The oscillator is now switched on. The amplitude of vibration of the oscillator is constant. The frequency f of the vibration of the oscillator is varied. The oscillator is forced to oscillate by means of vibrations of the oscillator. So the troll is forced to oscillate by means of vibration of the oscillator. In other words, now the troll is going to vibrate under the influence of an oscillator. So it's now forced oscillations. The variation with the f of the amplitude A naught of the oscillations of the troll is shown here. So this is the resonant curve. By reference to your answer in A, state the approximate frequency at which the amplitude is maximum. Of course, that is going to be automatically 2.5, because remember, amplitude is maximum when the natural frequency equals to the driving frequency. So this is the natural frequency when there is no oscillator. So it means when the frequency of the oscillator arrives at 2.5, then the trolley absorbs maximum energy and vibrates with the maximum amplitude. So the maximum frequency, the frequency at maximum amplitude must be 2.5. The amplitude of the oscillations in B may be reduced without changing significantly the frequency at which the amplitude is maximal. State how this may be done and give a reason for your answer. You may draw on the figure if you wish. So without significantly changing the frequency, we can change that amplitude by doing what? They told us we can even draw on the figure 2.1. Figure 2.1 is not that graph. The graph is figure 2.3. This is figure 2.1 is this one. So we can reduce the amplitude of vibration. Maybe, for example, we can attach a card. We can attach a card on the trolley. This is a card. If I attach a card on the trolley, what would be happening? I've increased the surface area over which friction or air resistance is going to act. And if I increase the surface area over which air resistance is going to act, it means I have reduced the amplitude of vibration. So it means the system has actually been more damped. Okay, so if I want to put this in explanation, I will simply say attach a sheet of card attach a sheet of card to the trolley. And this is of course to increase damping or to increase friction force. To increase damping or air resistance or friction. Alternatively, you could also reduce the oscillator amplitude. Of course, when we reduce the oscillator amplitude, we are reducing the energy input to the system. So the frequency is going to decrease. So reduce the oscillator amplitude. When we reduce the oscillator amplitude, this reduces the energy input to the system. It reduces the energy input to the system, and therefore, if the energy input to the system is reduced, then the amplitude of oscillations are going to reduce. We have reduced the amplitude of the oscillator itself. So this is going to reduce the amplitude of oscillation of the trolley. Okay. The most direct one is attaching a sheet of card to the trolley so that there is a large surface area for air resistance to act. That increases friction. So that means it is increasing damping. It is increasing damping. A ball is held between two fixed points, A and B, by means of two stretched springs as shown here. The ball is free to oscillate horizontally along the line AB. During the oscillations, the springs remain stretched and do not exceed their limits of proportionality. That means Hooke's law is still obeyed. The variation of the acceleration A of the ball with its displacement x from its equilibrium position is shown here. We are familiar with this graph of acceleration against time. So first of all, we can check and see that the amplitudes are the same. So this is 2.8 negative. You can also see this side is also 2.8 positive. We can check the maximum acceleration. This one is, here it is 5 divided by 10, 0.5. So this is going to be 17, I think, 0.5. 18, 18.5, sorry, 14.5, not 17. I think this is 14.5 maximum acceleration. Let me check here. It is also 14.5 maximum acceleration. Okay. So the first question is, state and explain the features of the figure that indicates that the motion of the ball is simple harmonic motion. We have seen it is a straight line through the origin. So number one, straight line through the origin. Straight line through the origin shows that acceleration is directly proportional to displacement. A straight line through the origin shows that the acceleration is directly proportional to displacement. Number two, we also see that from the line, the gradient of this line is negative. This is a negative gradient. A negative gradient, it brings in the minus sign. A negative gradient indicates that the acceleration and the displacement are always in opposite directions. So negative gradient shows that acceleration and displacement act in opposite directions. Okay. Use the figure to determine for the oscillations of the ball the amplitude. Of course, the amplitude, I just looked at the figure. The highest displacement here was 2.8. So the amplitude is 2.8. Maximum displacement 2.8. Then the frequency, of course, we can use a simpler method of using the expression acceleration is equal to negative omega squared x to find the frequency, or we can find the gradient. I will start with the gradient. So we know that the gradient is going to be equal to omega squared, because note that acceleration equals to negative omega squared x. We have plotted a graph of A against x. So the gradient is going to be equal to, of course, the gradient itself is negative. So the gradient is equal to omega squared. And we know that omega is 2 pi times f. So I'll find a gradient. Since the line goes through the x-axis, then it is very easy to find a gradient. So the gradient is, let me check. What is this? 14.5. Let me check again. 1, 2, 3, 4, 5, 6, 7 times 0 0.5. 7 times 0 0.5. No, it is 13.5. So I'm just finding the gradient by taking the line from where it starts from, the highest point, that is 13.5 minus 0, divided by the y that is going to be 2.8 minus 0, because it goes through the origin. Remember, the x values are times 10 power negative 2, because it is in centimeters. The acceleration is in its SI units, so I will find the gradient as, the gradient is going to be 13.5 minus 0 divided by 2.8 minus 0, but this one is times 10 power negative 2. And the gradient is 13.5 divided by 2.8 exponent negative 2. So the gradient is 482, and this is going to be equal to 2 pi f. So it means 2 pi f should be equal to 482. What is pi? Divided by, what is f? So 482 divided by 2 pi, 2 shift pi, and this is 70, is it? No, this was omega squared, by the way, not, this was squared. 2 pi squared is equal to 482, because remember, gradient was omega squared, and omega alone is 2 pi f. So I had to find the square root first. 2 pi f, I first find the square root of 482, root of 482. Then I divide the root by 2 pi. And I'm getting 3.49. So f is 3.49, which is approximately 3.5 hertz. Alternatively, I could use the formula directly. Acceleration is equal to negative omega squared x. I just take a value for acceleration and its corresponding value of x to give me omega, and then I equate omega to pi f. So it's the same as taking this gradient, because if I take a value of acceleration as 13.5 equaling to negative omega squared times the x value, know that when the acceleration is positive, the displacement is negative, because they are in opposite directions. So if I take this is going to be times negative 2.8. So this is giving omega squared as 482. Then I find the square root. So it is giving me omega squared as 482. Then find the square root. Remember, omega is 2 pi f. So you find the square root and you'll be able to find f. So 2 pi f, and this is squared, is also 482. So you'll get f as 3.5 still. Okay. The arrangement in the figure is now rotated through 90 degrees so that the line AB is vertical. The ball now oscillates in a vertical plane. Suggest one reason why the oscillations may no longer be simple harmonic motion. So we are assuming We are assuming now the system is like this because it's rotated through 90 degrees. So the system is now vertical like this. Of course, here there is going to be weight of this ball acting vertically downwards. So it means the lower spring may not be extended, yet the upper spring may be extended beyond the elastic limit. So we can simply say this may no longer be a simple harmonic motion because the lower spring may not be extended, it will simply be compressed. The lower spring may not be extended, or we can look at the upper spring. It may be stretched beyond the elastic limit. Or the upper spring, because of gravity, the upper spring may exceed the limit of proportionality. Therefore, the oscillations may no longer be simple harmonic motion. Here we have a metal ball that is suspended from a fixed point by means of a string as shown here. The ball is given a small displacement and then released. The variation with the time t of the displacement x of the ball is shown here in the figure. So here we have a figure for the displacement against time for the ball. State two times at which the speed of the ball is maximum. Remember in the previous question, one of the previous questions we have said when displacement is maximum, the speed is zero. When the displacement is zero, the speed is maximum. State two times at which the speed of the ball is maximum. So we look for points where the displacement is zero because the speed is only maximum when the displacement is zero. In other words, this is a graph of gradient against time. I mean the graph of displacement against time, and the gradient is the velocity or the speed. So the gradient is maximum when the line is just crossing the x-axis. But note that at 0.4 and 1.6 the gradient is the same and the same direction, it is positive, and at 0.8 is going to be negative. So here at 0.4 and 1.6 speed is maximum and in the same direction, but in the opposite direction to the one at around here, not 0.8 but close to 0.8. So let's find this time first. Let's know the scale. The scale on the vertical axis, we need the scale on the x-axis. It is 0.4 divided by 10 small squares, that is 0.04 each small square. So let's count the number of small squares until we reach the point where the graph crosses the x-axis. So this is 1, 2, 3, 4, 5, 6, 7.5. So I multiply this by 7.5 to get that time. So 0.04 times 7.5. So that is 0.3. The first time is 0.3, where speed is maximum. Then there is also this time here, although they are in opposite directions, I'll also find it. So this is 2.5 small squares from 0.8. So 2.5. I multiply 2.5 times 0.04. 2.5 times 0.04. That is 0.1. So I add it to 0.8. That becomes 0.9. Another one is here. These are how many small squares from 1.1, 2, 3, 4, 5, 6, 7.5. Remember 7.5 was 0.3. So I add 0.3 to 1.2. That gives me 1.5, and so on and so forth. You can even predict the next. You can predict the next, but these ones can be seen from the graph. If you want to predict the next, you can check 2.10. But of course, 2.1 is not on the graph. It is not seen on the graph, but it can be predicted. Okay, show that the maximum speed the maximum speed of the ball is approximately 0.08 meters per second. Maximum speed. Remember, speed is maximum when the displacement is 0. And we saw from the equation V equals to omega square root of x naught squared minus x squared. V maximum is equal to omega times x naught. This one will be 0. So maximum speed V is equal to omega times x naught. And we know that omega is equal to pi f, which is 2 pi over t. So omega is going to be 2 pi over t. We find a period here. We can find a period. I'll use this point as the reference point and this one. So here at the center, I think this is 1, 2, 3, 4, 5. That should be 0.6. And this is 1, 2, 3, 4, 5. So this is going to be 1.8. So 1.8 minus 0.6, that is 1.2. So the period is 1.2 seconds. So I'm substituting maximum velocity V naught is going to be equal to 2 pi over 1.2 times the maximum displacement from the graph. Maximum displacement is 1. I think that is 1.5. 1, 2, 3, 4, 5. 1.5 in centimeters, so it is times 10 power negative 2. And when I press my calculator to check, I'm getting 0.079. 0.079. You can verify and see. Another method will be to find a gradient at the point where the graph crosses the x-axis. The other method would be to find a gradient at the point where the graph crosses the x-axis. That can be your assignment. You just try to draw a tangent at one of these points where the graph crosses the x-axis. You draw a tangent and you try to find the gradient of that tangent. Imagine you draw a tangent here and you try to find the gradient of that tangent. You try to find the gradient of that tangent. Maybe let's try this. This point here and this, I'm using that point and that one. The gradient is equal to the y values. I have this as 0.7 minus negative. This is 1, 2, 3, negative 0.7. This is going to be times 10 power negative 2 divided by the x values. This is 1, 2, 3, 4, 5. That is 5. And this is at 0.4. 0.4, so that is a half. I think that is 0.2. So that is 0.2. 0.7. So for the gradient, it will give you approximately 0.7, because that is 1.7 divided by 0.2. Is it true? No. 1.4 divided by 0.2. So for gradient to give you approximately 0.07, and I think that will be acceptable. You just look at 0.08 plus or minus 0.01. meters per second. Your gradient should be in that range, so 0.07 is going to be acceptable. Okay, so the gradient will also be accepted. The variation with the displacement x of the potential energy EP of the oscillations of the ball is shown in the figure here. So this is potential energy. We see that potential energy is 0 when displacement is 0. And we see that potential energy is maximum when the displacement is maximum from the graph. We know that potential energy is equal to a half m omega squared x squared. It is actually directly proportional to the displacement squared. On the axis of the figure, sketch a graph to show the variation with displacement x of the kinetic energy. Of course, when the potential energy is 0, kinetic energy is maximum. So it means the first point will be here. When potential energy becomes maximum, kinetic energy is 0, so the second point will be here and the third one is here. So we're just going to draw the, can I call it a reflection? Let me first try to reduce this size. So we are going to draw a graph of kinetic energy, and they are going to cross each other at the center of the maximum energy. So that is 25 divided by 2, which is 12.5. So these lines should cross at 12.5. So the scale on the vertical is 5/10, 0.5. So this is 11, this is 12, and I think this is 12.5. Each small square is 12.5, so the graphs should cross around here. Okay, so I'm now sketching the graphs. You can sketch a better one than mine because me, I'm sketching on a computer. As simple as that. Where the graph crosses is the most important part. Okay, so it is just very important for us to note that these graphs are going to cross at energy of 1.5 millijoules. That's at the point where the kinetic energy is equal to the potential energy. That is half. And when potential energy is maximum, kinetic energy is 0. When potential energy is 0, kinetic energy is maximum. So you should be able to sketch such a graph. So on the axis of the figure, sketch a graph to show the variation of displacements of kinetic energy. So that when we have finished, the amplitude of the oscillations reduces over a long period of time. After many oscillations, the amplitude of the oscillation is 0.60 centimeters. Use the figure 3.3 to determine the total energy of the oscillations of the ball. For oscillations of the amplitude 0.6. So we want to determine of total energy of the oscillations of the ball. So we know that at maximum amplitude, potential energy is equal to total energy. At maximum amplitude, At maximum amplitude, total energy is equal to the potential energy. At maximum amplitude, we know that the total energy will be equal to the potential energy. So we want to use the figure to determine the total energy of the oscillations of the ball for oscillations of amplitude 0.60 centimeters. Explain your working. So at maximum amplitude, total energy is equal to the potential energy. So first of all, we have already seen that when x is 1.5, the energy when maximum amplitude was 1.5, the potential energy is 0, or we can simply use an expression for potential energy. So energy is equal to a half m omega squared x naught squared. At maximum amplitude, total energy is the potential energy. So energy is going to be equal to a half m omega squared x naught squared. We know that when we had amplitude as 1.5, total energy was 25 millijoules. So I'll simply say 25 millijoules was equal to a half m omega squared. Amplitude was 1.5, and this is squared. Then we want the energy, total energy, when the amplitude is 0.6. So I'll just say x, or I'll just write there E for energy will be equal to a half m omega squared, and this is going to be 0.60, and that is squared. So I'm going to combine the two equations, and you notice that energy is going to be equal to, when I divide the two equations, so energy is going to be equal to 0.6 over 1.5, and this is squared, times 25 millijoules. So we have 0.6 divided by 1.5 squared times times 25, and this is giving me 4.0 millijoules. So I just consider the situation, the first case from the graph, where we saw that when the amplitude was maximum 1.5, the maximum energy was 25. Then we check if the amplitude is 0.6, what is the maximum energy? So I just combined into these. I just formed two equations and solved them by dividing. Of course, when I divide the second equation by the first one, a half m omega squared cancels out. So I remain with 0.6 over 1.5 squared, then times 25, because I'm cross multiplying. So the answer here is 4.0 millijoules. 4.0 times millijoules, or 4.0 times 10 power negative 3. Times 10 power negative 3 joules. A small ball rests at a point P on a curved track of radius r, as shown here. So we see the curved track. The ball is moved a small distance to one side and is then released. The horizontal displacement x of the ball is related to its acceleration a towards p by the expression a is equal to negative gx over r. G is the acceleration of free fall. Show that the ball undergoes simple harmonic motion. There is no calculation here. You just look at the graph. First of all, not at the graph, but the equation a is equal to negative gx over r. When you look at the graph, at the equation, you will notice that actually g is acceleration of free fall, which is a constant, and r is the radius, which is also a constant. So g and r G and R are constants, or G over R is a constant. G and R are constant, so acceleration is directly proportional to displacement. So that's one. Number two, in the equation you see that there is a minus sign. What does that indicate? The minus indicates that acceleration and displacement are always in opposite directions. So the negative sign indicates or shows, the simplest word is shows. The negative sign shows that acceleration and displacement are always in opposite directions. And those two are the defining conditions of a simple harmonic motion. So the motion is simple harmonic. The radius r of a curve of the track is 28 centimeters. Determine the time interval t between the ball passing point P and then returning to point P. So we have already seen that acceleration equals to negative g over r times x. Compare with the general defining equation. Acceleration is equal to negative omega squared x. When you compare, you see that omega squared is equal to g over r. Omega squared is g over r, so we just substitute. What is g? G is acceleration due to gravity, which is 9.81. And the r is the radius of the track, which has been given as 28 centimeters, which is 28 times 10 power negative 2. So that is omega. But I want you to also recall that omega is 2 pi. Omega is 2 pi over t, which means t is 2 pi over omega. So I will just substitute here. It means omega squared is going to be 2 pi squared over t. So I have that 9.81 over 28 times 10 power negative 2. This should be squared, should be equal to, no, omega squared is going to be 2 pi over t squared. So this is going to be equal to 2 pi over t, and then that's squared. So I'll begin by dividing. I find the square root. 9.81 divided by 28 exponent negative 2 square root. Then I get 2 pi divided by that. So it means t is going to be 2 pi divided by the square root of 35. So t is equal to 1.06 seconds, but that's not the answer. Here we want t. Determine the time interval t between the ball passing point P and returning to point P. I think that is half a cycle. Let's say it passes point P, it goes to that extreme end, and it just comes the second time. That is half a cycle. So t is half a period, because it's half a cycle. So tie is going to be 1.06 divided by 2, which is 0.53. So that is 0.53 seconds. The variation with the time t of the displacement x of the ball in B is shown in the figure. So that is displacement with the time. Some moisture now forms on the track, causing the ball to come to rest after approximately 15 oscillations. On the axis of the figure, sketch the variation with the time t of the displacement x of the ball for the first 2 periods after the moisture has formed. Assume the moisture forms at time t equals to 0. So they are saying after some time moisture forms and the ball comes to rest after 15 oscillations. So it means the amplitude is just going to gradually decrease. But the frequency, since the period is going to remain the same, the frequency is the same, the period is remaining the same. So what is going to be changing is the amplitude. So gradually the amplitude is going to reduce. So that is the first period. They cross through, it must go through the same time. So that is for the first period. That is for the second period, and so on and so forth. So what is very important is to note that the amplitude gradually reduces. Okay, so the amplitude gradually reduces. It is undergoing light damping. So we have finished to sketch the new variation with time of the displacement. A light spring is suspended from a fixed point. A bar magnet is attached to the end of the spring as shown here. Here we have a cardboard cup. In order to shield the magnet from draughts, a cardboard cup is placed around the magnet but does not touch it. The magnet is displaced vertically and then released. The variation with time t of the vertical displacement y of the magnet is shown here. So here we have variation of displacement y with time t. The mass of the magnet is 130. For the oscillations of the magnet, use the figure to determine the angular frequency omega. At this point, we now know that angular frequency omega is simply 2 pi f, or 2 pi over t. It is simply 2 pi over t. So we can look for the period from the graph. And from the graph, if I start at t equals to 0, then the first period is there. Or I consider this is, I think, 0.3, 15. And this is, I think, 0.45. When I subtract, I get 0.3. 0.45 minus 0.15, that is 0.3. So the period is 0.3. I just press my calculator. So this is 20.9. You can also verify. Show that the maximum kinetic energy of the oscillating magnet is 6.4 millijoules. Maximum kinetic energy is the same as maximum energy. So maximum kinetic energy will be half m omega squared x naught squared, since it is maximum. Or you could use a half mv squared, but remember v will be omega x naught. So this is going to be a half. The mass was 130 grams, I guess. 130, so that would be 130 times 10 power negative 3. Then omega, we have got omega as 20.9, so this would be 20.9. If you want, you can put there 2 pi over 0.3. I'll just put there 20.9, and this is squared. Then maximum displacement or amplitude from the graph, and I think this is 1.5. That is 1.5. So times 1.5 times 10 power negative 3, no, negative 2, because it's in centimeters. And this should also be squared. So I press my calculator to verify. So this is 6.4 times 10 power negative 3 joules. That is approximately 66.4 millijoules. I'm saying you can use kinetic energy as a half m v squared, but this is maximum velocity, and maximum speed is equal to omega times x naught, which takes you back to the same expression. The cardboard cup is now replaced with a cup made of aluminium. Of course, now this is a conductor. During 10 complete oscillations of the magnet, the amplitude of vibration is seen to decrease to 0.75 centimeters, shown in the figure 1.2. The change in angular frequency is negligible. Use Faraday's law of electromagnetic induction to explain why the amplitude of oscillation decreases. Of course, we are seeing the cardboard is replaced by an aluminium foil, which is a conductor. So when as the magnet oscillates in the metallic cup, in the aluminium foil cup, of course, the cup will be cutting or will be intercepting the magnetic field lines of the oscillating magnet. By Faraday's law, an EMF is going to be induced in the aluminium cup, and that EMF is going to create eddy currents in the aluminium cup. The eddy currents are going to dissipate energy as thermal energy in the aluminium cup, and remember that energy came from the oscillations of the magnet, so the oscillations are going to die out. Alternatively, you can think about Lenz's law, where the magnetic field which is created in the aluminium cup also tends to oppose the magnetic field of the magnet, decreasing the oscillations of the magnet. So we can simply say, I will start with the simplest side. So as the magnet moves, as the magnet moves, flux is cut by the aluminium cup. Flux is cut by the aluminium cup, of course, by Faraday's law. This gives rise to an induced EMF. Even if I don't mention Faraday's law here, giving rise to an induced EMF. In the cup. The induced EMF gives rise to eddy currents. The induced EMF gives rise to eddy currents and heating of the cup. Because the eddy currents are going to cause energy to be dissipated in the cup as heat. This thermal energy which is heating the cup has been derived from the oscillations of the magnet, so amplitude must decrease. So this thermal energy is derived from oscillations of the magnet. So the amplitude reduces. So amplitude decreases. Alternatively, as the magnet, the other part will remain the same. I'll just use a different color. Alternatively, as the magnet moves, flux is cut by the aluminum cup, giving rise to an induced EMF in the cup. Okay? So we now want to use a different way of looking at this. So this time the induced EMF is going to give rise to a current, which current generates another magnetic field. So we can also say the induced EMF gives rise to currents which generate a magnetic field. So the induced EMF in the cup again also is going to create a current, which a current again generates a magnetic field in the cup. This magnetic field is going to oppose the magnet according to Lenz's law. So the magnetic field opposes motion of the magnet. So the amplitude decreases. So this is another way of looking at it. We can look at the induced current, the induced EMF giving rise to eddy currents, which generate another magnetic field. Of course, the generated magnetic field, according to Lenz's law, is going to act to oppose the change causing it, which is now the motion of the magnet. So the amplitude will decrease. So that one, although it is in simple harmonic motion, we discussed it in details under magnetic fields and electromagnetic induction. Okay, show that the loss in energy of the oscillations of the oscillating magnet is 4.8 millijoules. So we know that energy is equal to a half m omega squared x naught squared. That is maximum energy. And we have two values of x naught. We have two values of x naught, not necessarily two values of x naught. We have x naught as 0.75, and what was the initial amount of energy? The initial amount of energy was, what was the initial amount of energy? The maximum kinetic energy of the oscillating magnet was 6.4. Okay. Let's find the energy at 0.75 and subtract it from 6.4 to see if we get 4.8 millijoules. So energy at x naught equals to 0.75 centimeters. Energy is going to be equal to a half. The mass was 130, I guess. The mass was 130 times 10 power negative 3. Omega was 20.9 if it did not change, squared. And x naught is 0.75 times 10 power negative 2, and this is also squared. I'll check my calculator for this energy. So this is 1.6 millijoules, or 1.6 times 10 power negative 3 joules. So we want to find the loss. So loss in energy is going to be 6.4 millijoules minus 1.6 millijoules, which I think it is 4.8. If you're a math student, you can do this using simple mathematics relations. We notice that energy is directly proportional to x naught squared. Energy is directly proportional to x naught squared. And we notice that 0.75 was actually half of 1.5. So in other words, the amplitude is halved. If x is halved, E is reduced by a quarter. So since if x equals to a half of x naught, of the original value of x naught, then energy is going to be, because it is directly proportional to x naught squared, it is going to be a quarter of the original value of energy, which will be a quarter of 6.4, which I think is 1.6. That is the new value of energy, and then we now subtract it from the original value. Okay, but that, I know we have fewer mathematicians here. Simpler substitution in the expression will still give you the same answer. The mass of the aluminium cup in B is 6.2 grams. The specific capacity of the aluminium is 910. The energy in B is transferred to the cup as thermal energy. Calculate the mean rise in temperature of the cup. So this energy here is transferred to the cup as thermal energy. So it causes a change in temperature. And you know that amount of heat which causes change in temperature is given by mc delta change in temperature. So we shall have that 4.8 times 10 power negative 3, that is the energy, should be equal to the mass of the cup, which is 6.2 grams, that is times 10 power negative 3, then times the specific heat capacity, which is 910, times the change in temperature, delta theta. What is delta theta? So from my calculator, delta theta is 8.5 times 10 power negative 4. 8.5 times 10 power negative 4. You can also verify with your calculator. Distinguish between free oscillations and forced oscillations. Remember, free oscillations, the body oscillates without any loss or gain in energy. No loss, no gain in energy. That means no external forces are applied. No loss or no gain in energy, no external resistive forces applied. No resistive forces or no external forces are applied. So for free oscillations, the body oscillates without loss of energy. The body oscillates without loss of energy since the body oscillates without loss of energy or without loss or gain. Loss or gain of energy since no resistive forces or external forces act. So there is no any other force acting to use the energy of the system or to add energy to the system. So the body oscillates without loss or gain in energy. That is free oscillations. For forced oscillations, then we have to supply the body with a certain amount of energy so that we keep it vibrating for a required period of time. So in other words, the body is going to be made to vibrate by an external periodic force continuously. So here, continuous energy is input, continuous energy input. There is continuous energy input, or continuous energy input is required to cause the body to vibrate or to oscillate for a required period of time. So there is a continuous energy input so that the body is made to vibrate by an external periodic force. So the body is made to vibrate by an external periodic force. The body is made to oscillate by an external periodic force, or you can call it a driving oscillator. You can call it a driving oscillator. I think the oscillator is OS. So there is a driving oscillator. There is a system which is going to supply a continuous amount of energy, which I'm now calling a driving oscillator, so that a given body is made to oscillate by an external periodic force over a required period of time. The frequency with which it oscillates is going to be the forced frequency. A trolley is held on a horizontal surface by means of two stretched springs, as shown here. One spring is attached to the fixed point, the other spring is attached to an oscillator that causes horizontal oscillations of the trolley. The oscillator vibrates with a constant amplitude of vibration. The frequency of vibration of the oscillator is gradually increased from a very low value. The variation with the frequency f of the amplitude x naught of the vibration of the trolley is shown in the figure here. So this is a resonant curve. Use the figure to state and explain the value of the natural frequency. Of course, we just look for the maximum amplitude. So the natural frequency is 2.1 because the scale here is 1.5, 2.0, that is 0.5 divided by 10, which is 0.05. Each small square is 0.05, and there are two small squares here, so that is 2.1. So the natural frequency is 2.1. So F is 2.1. They said state and explain the value. So I'm saying F is 2.1 Hertz. We know that resonance occurs when the natural frequency is equal to the driving frequency. When the natural frequency is equal to driving frequency, and this results in maximum amplitude. Resulting in maximum amplitude. So where we see maximum amplitude, that should be a point where the natural frequency is equal to driving frequency. So the natural frequency is 2.1. Use the figure again to state and explain whether there are any frictional forces acting on the trolley. Of course, there are frictional forces. If they were not there, then this would be a straight sharp line, and this would also be a straight sharp line. So there is some damping. That's why you see the peak is not infinite. So the peak is not very sharp. The peak is not very sharp. The peak is not very sharp, which means the amplitude is not infinite. The amplitude is not infinite. So frictional forces are present. Therefore, there is damping. So frictional forces are present. Frictional forces are present. That means there is some damping, although it could be light damping. If there was no light damping, the amplitude would be finite, infinite. In other words, we shall have just one amplitude here, but you see here there is a range, a small range. So that means the peak is not infinite, or the peak is not very sharp. So the amplitude is taking on such a small range of frequencies. The oscillator is now stopped. So we go back to the natural frequency. The trolley is given a horizontal displacement of 4.7 centimeters, so this is going to be our x naught. Along the line of the springs, the trolley is then released. Use the information from figure 4.2 to estimate the maximum speed of the trolley. So in 4.2, just go the natural frequency, which was 2.1. So we want the maximum speed, V naught, is equal to omega times x naught. Remember, omega is 2 pi f, so this will be 2 pi f times x naught. So that will be 2 pi times f, which is 2.1, times x naught, which is 4.7, times 10 power negative 2, because it is in centimeters. Just check my calculator. So from my calculator, this is 0.62 meters per second. A tube sealed at one end has a circular cross-sectional area A 4.9 times 10 power negative 4 meters squared. Some sand is put in the tube so that the total mass M of the tube and its contents is 70 grams. The tube floats upright in a liquid as shown here. The liquid has density ρ as 0.79 grams per centimeters cubed. By reference to the liquid pressure, pressure in liquids is H rho G, that is from AS. By reference to the liquid pressure exerted on the base of the tube, show that the distance h of the base of the tube below the liquid surface is 18 centimeters. Explain your working. So we know pressure is equal to H density times G. Pressure is going to be H times density times G. But note that H times density remember, density is equal to mass over volume. So density is mass over volume. Density is going to be equal to mass over volume. And this will be mass. Volume is going to be the cross-sectional area times the height h. Volume is cross-sectional area times the height h. Remember, a body displaces a value which is a volume which is equal to its own volume. So it means that pressure can also be given as m times, I'm replacing the density, so I get m over cross-sectional area A. Okay. The mass was actually, what is the mass? The mass is 70 grams. The mass is 70 grams. The cross-section area is 4.9. The density is 0.79. So I can just say H times density times G is equal to mg over cross-section area A. So I have that H times density times G is the same as mg over the cross-sectional area. So I want H. So I'll say H times the density. The density is 0.79 grams. This is the same as times 1,790 kilograms per meters cubed. So that is 790 times. Of course, G has cancelled. G is useless here. So this will be now times the cross-sectional area. The cross-sectional area was 4.9 times 10 power negative 4. This should be equal to the mass. And the mass was 70 grams, which is 70 times 10 power negative 3. Okay. I've done a lot of mathematics here just to show you that there is a relationship between all these. Okay, so alternatively, I could look at this as pressure being force over area or the weight over area and equate it to this expression here. I'm trying to find h. Just divide both sides from my calculator. 70 exponent negative 3 divided by 790 divided by 4.9 exponent negative 4. So I'm getting h as 0.1808, which is approximately 18.1 centimeters or 18 centimeters. The tube in B is displaced vertically and then released. The variation with the time t of the distance h is shown here. So you see it is decreasing. A system oscillates with simple harmonic motion of angular velocity, angular frequency, omega, given by this expression, where g is the acceleration of free fall. Use data from B to determine the time t1. What is t1? You notice that t1 is half a period. T1 is half a period, so what do? We need to find the period first. So omega squared is equal to that. So omega squared is going to be density was 790. Cross-sectional area was 4.9 times 10 power negative 4. G is 9.81. Divided by M was 70 times 10 power negative 3. I'm trying to find omega squared. So I will find the square root directly. So what is omega? 790 times 4.9 exponent negative 4, 981. So under the square root, finding the square root, omega is 7.37 radians per second. That's omega, but remember omega is 2 pi over t. Omega is 2 pi over t, meaning that t is going to be 2 pi over omega, which is 7.37. And what is t? Remember, t is the time for one cycle, which is the period. So divide by 2 pi divided by that. 2 pi divided by that, I'm getting 0.85 seconds. Remember, t1 is a half of a period from the graph. This is half a cycle. When I come back here, that will be a complete cycle at t2. So t1 is half a cycle. So I'm going to divide the period by 2. Check 2 pi divide by 7.37 divide by 2. So this is approximately 0.43 seconds. Then T3. You see that T3 is one cycle plus a half. I think that is an easy question. T3 is one cycle and a half. So T3 is equal to period plus half a period, which is going to be 0.85 plus 0.43, which is going to be, that is 1.28, as simple as that. Determine the loss in total energy of the oscillating system between time t equals to 0 and time t equals to t4. Loss in energy between time t equals to 0 and t equals to 4. So energy is equal to a half m omega squared x naught squared. So the loss is going to be just the change. So I'll just simply say that change in energy is equal to a half. The mass was 70 grams, so that is 70 times 10 power negative 3. We have seen omega, I think I calculated omega at 7.35. Omega squared was, this value here was 54, I think it was 54.25. Or you can square 7.37, no problem. So omega is 7.37 and this should be squared. Now there will be a change in the values of x naught. At t equals to 0, x is 20 point what? So the scale here is 2 over 5, that is 0.5. No, it is 1 over 5. 1 divided by 5, which is 0.2. So it is 20.2. Is it 20.2? So this is 20.2. subtracted from, so 20.2 minus 18. What do you get? 20.2 minus 18, that is 2.2. So the amplitude, of course, with the amplitude, this is the equilibrium position, so that's why I'm subtracting 18. Or I can take this value here at the bottom. Unfortunately, this is at the center, it is not the amplitude that equals 0. So here it is 20.2 centimeters, equilibrium is at 18. So this is going to be 20.2 minus 18, that is 2.2 times 10 power negative 2, because it is in centimeters, minus the other one, that is at t equals to t4. At t equals to t4, this is, I think that is 19. Is it 19? Minus 18. So 19 minus 18, that is 1 centimeters. So this is going to be minus 1.0 times 10 power negative 2. And this is also squared. I know people will use 20.2 as x and then 19 as x. Not at all. We are taking measurements of the displacement from equilibrium. At equilibrium, h is 18. So above equilibrium, it goes up 22.2, and then it also goes below equilibrium. So now I'll press the calculator once without even wasting time. So without wasting time, I go to the calculator. Loss difference in energy as 7.3 times 10 power negative 4. So that is the loss in energy. So the relation between omega and F. Of course, we know that omega is equal to pi times F. Significance of the minus. The minus has always been showing that acceleration and displacement are always in opposite directions. Acceleration. Oh, since here they have given us a and x, we can say a and x are in opposite, not different, it is opposite directions. Oh, a is always directed, so acceleration and displacement are always in opposite directions. Or acceleration is always directed towards equilibrium position or towards the mean position. A frictionless trolley of mass m is held on a horizontal surface by means of two similar springs, each of spring constant k. The springs are attached to fixed points as illustrated here. When the trolley is in equilibrium, its extension is E. So it means when it is in equilibrium, tension is Ke. The trolley is then displaced a small distance x to the right. So it is given a small distance x to the right. The extension this side will be now E plus x. The extension this side will now be E minus x, because it is displaced this side. One compresses, the other extends. So we can now find the tensions in the springs. Tensions in springs. The tensions in the springs are going to be, for the first spring, T1, let this be T1, the other one be T2. So T1 is going to be K into E plus X, and T2 is going to be K into E minus X. So the resultant is the difference in those two tensions. The resultant force is going to be equal to K into E plus X minus K into E minus X. So this means the resultant force F is going to be equal to twice kx. The trolley is then released. Show that the acceleration of the trolley is given by that expression. So by Newton's second law, we know that the resultant force F is equal to mass times acceleration. And then the force is going to be equal to negative 2kx. We explain the minus. The minus sign indicates force is in opposite direction to displacement. So we now substitute m times a is equal to negative 2kx, which when we simplify, of course, we divide both sides by m. The acceleration a is going to be negative 2kx divided by m as required. So do not forget to define the minus. It is the most important marker there. The mass m of the trolley is 900 grams and the spring constant is 120 newtons per meter. By comparing the equations in A and B Roman 2, determine the frequency of oscillations. In B Roman 2, we have this equation here, and in A, we have that acceleration is equal to negative omega squared. So it means omega squared is going to be 2k over m if we compare the two equations. So omega squared is equal to twice k over m. And we want the frequency. Remember, omega is 2 pi f. So we simply say that 2 pi f squared is equal to 2k, that is 2 times 120 over m, which m is 900, which is 0.9. So I get that I say 120 times 2 divided by 0.9 square root, and I divide by 2 pi. So f is equal to 2.6. Okay, define the radian. You must have seen the radian in circular motion, but because angular velocity here is being given in radians per second, the unit radian can also come here, the radian. So the radian is like the angle subtended at the center of the circle, where the arc length is equal to the radius. Remember, the arc length delta theta, the angle delta theta is equal to s over the arc length over the radius. If s and r are equal, then delta theta is 1 radian. So the angle subtended at the center of a circle where the arc length is equal to the radius. The arc length is equal to the radius. State by reference to simple harmonic motion what is meant by angular frequency. Of course, angular frequency omega is simply going to be defined by 2 pi over period according to simple harmonic motion, or it is 2 pi times frequency. As simple as that. Angular frequency is 2 pi times the frequency. Remember, angular frequency is omega. So that is the simple meaning of angular frequency. A thin strip, metal strip, clamped horizontal at one end, has a load of mass m attached to its free end, as shown here. So we see the strip is displaced through a distance x. When the free end of the strip is displaced vertically and then released, the mass oscillates in a vertical plane. Theory predicts that the variation of the acceleration a of the oscillating rod with the displacement x from its equilibrium position is given by this expression, where L is the effective length of the metal strip and C is a positive constant. Explain how. The expression shows that the load is undergoing simple harmonic motion. Just this expression here. Number one, what is C? What is C? L is the length of the strip, which is not changing. C is a positive constant. And M was the mass of the load, which is also not changing. So it means C over M L cubed is a constant. C over L M L cubed is a constant. What does that mean? So acceleration is directly proportional to displacement. That's number one. Number two, we see a minus sign here. So the minus sign indicates that the acceleration and displacement are always in opposite directions. So the acceleration and displacement are always in opposite directions. Okay, so these two satisfy that the motion is simple harmonic. For a metal strip of length of 65 centimeters and a load of mass 240 grams, the frequency of oscillation is 3.2. Calculate the constant C. So when you compare the equation A equals to negative C over M L cubed X with the general equation A equals to negative omega squared X, you notice that omega squared is going to be equal to C over M L cubed. And remember, omega is 2 pi F. So we shall simply say 2 pi F is equal to C. This should be squared. Is equal to C over M L cubed. So I'm substituting and I'll find the square root because I want to find C anyway. So I'll just say 2 pi times F. F is 3.2. This should be squared times, I'm making C the subject now. M, 240 grams, 240 divided by 1000, that is 0.24 times L. L is 65 centimeters, divided by 100, that is 0.65, and this is raised to power 3. This should be equal to C. I just cross multiplied. So I'll check my calculator. So from my calculator, C is 27. Since I changed all the quantities to their units, then this unit is correct. So C is 27. A thin metal strip is clamped at one end so that it is horizontal. A load of mass M is attached to its free end. The load causes a displacement S of the end of the strip as shown here. So we have almost the same question but slightly changed. The load is displaced vertically and then released. The load oscillates. The variation with acceleration A of the displacement S of the load is shown here. So we now have displacement against acceleration. It is a straight line. We just check if it stops at the same point for displacement. Yes. It should be having the same magnitude from the equilibrium position. Equilibrium is now 2. So this side, the acceleration was the same. Above 2, that is I think 1.5. Below 2, it's also 1.5. So that is simple harmonic motion I can predict. So from the graph, use the figure to determine the displacement of the load before it is made to oscillate. Before it is made to oscillate, we see it is crossing. The acceleration is 0 when the displacement is 2. The acceleration is 0 when the displacement is 2. It means it is it has a displacement of 2 before it is made to oscillate. So this means the displacement is 2.0 before it is made to oscillate. Then determine the amplitude of the oscillations. Now amplitude should be now maximum displacement from equilibrium position. So 2.0 is when it is in equilibrium. So amplitude above 2, we go to 3.5. So the amplitude is 3.5 minus 2, or it is 2.5 minus 1.5. So the amplitude is going to be 3.5 minus 2, or not, sorry, this is 0.5. 2.0 minus 0.5. So it means the amplitude is going to be 3.5 minus 2, or 2.0 minus 0.5, which gives us 1.5 centimeters. Show that the load is undergoing simple harmonic motion. Of course, yes. Number 1, it is a straight line. Although it doesn't go through the origin, the straight line indicates that acceleration is directly proportional to displacement. Number 2, the gradient is negative, which shows that the acceleration is in the opposite direction of the displacement. Number 3, the displacement from the equilibrium position is the same above and below. So that means it is simple harmonic motion. So we can say displacement from 2.0 centimeters, displacement from 2.0 centimeters, or displacement from 2.0 centimeter is the same on both sides. That means also the maximum acceleration is the same. So we have a straight line. Straight line shows acceleration is directly proportional to displacement. Number two, we have also seen that it is a negative gradient. So negative gradient shows that acceleration and displacement are in opposite directions. So it is simple harmonic motion. Displacement from 2.0. 2.0 is like the equilibrium position. Calculate the frequency of oscillation of the load. Frequency. So since it is a straight line, we can use the equation of simple harmonic motion directly. But alternatively, we know that if acceleration is equal to negative omega squared x, so the gradient is going to be equal to omega squared. So omega squared is equal to the gradient. Of course, the gradient is already negative. Omega squared is equal to the gradient, and it will be the negative gradient. Omega squared is going to be, no, the graph plotted is graph of x against a, so it's the other way around. Because it is x against a, this is not true, sorry for that. It is x against a. The easiest will be to choose a point and substitute. So x is equal to negative 1 over omega squared times a. So the gradient is going to be equal to negative 1 over omega squared. So which means omega squared should be equal to negative 1 over the gradient. So that is negative 1 over the gradient. Let's find the gradient then. So this will be negative 1 over, I'm finding the gradient. I'll just choose a few points here. So this is, what is this value? The scale is 2 over 10, 0.2. No, it is 1 over 10, that is 0.1. 3.1234. So that is 3.4 minus 2 divided by the acceleration. This is the scale here is 0.2 over 5, which is 0.04. So this is negative 0.8. So this is 0.84. So on the x-axis, I have negative 8.4, negative 0.84 minus 0. Taking this point and the vertical axis, find the gradient of that line. Okay, so this is going to give me a negative gradient. Let me check. 3.2 minus 2 divided by 0.8. Then 1 divided by the answer. Okay, so this is 3.4 minus 2.0 divided by negative 0.84 minus 0. This is the gradient. So the gradient itself is negative, of course. So this means omega squared is equal to negative 1 over the numerator of the gradient. I have 1.4 over negative 0.84, which gives us actually the negative has cancelled. So I have 0.84 divided by 1.4. Remember, the vertical axis was in centimeters. S was in centimeters, so I have to change this. This is supposed to be times 10 power negative 2 times 10 power negative 2 times 10 power negative 2. And I think this gives us 0.84 divided by 1.4. This gives us 60 as omega squared. That is 60. Remember, omega is 2 pi f. Omega is 2 pi f. So what does that mean? 2 pi f squared is equal to 60. And what is f? I first find the square root, then divide by 2 pi. When I divide by 2 pi, then I'm getting f as 1.2 hertz. 1.2 hertz. Let me check again. Root of 60 divided by 2 pi. Omega squared is 60. I find the root. Yeah, that is 1.2. I am saying if that is very hard for any of you, you can use the equation directly. You use A equals negative omega squared x, and you get a value of x and the corresponding value of A to give you omega. So get a value of A and its corresponding value of x to get omega. And when you get omega, then you will be able to find, of course, you can't use A equals to 0 and x equals to, that will not make any sense. Okay. To demonstrate simple harmonic motion, a student attaches a trolley to two similar stretched springs as shown here. The trolley has that mass. The trolley is displaced along the line of the two springs and then released. The subsequent acceleration is given by that expression there, where the spring constant K for each spring is 64 newtons per meter, and x is the displacement of the trolley. Show that the frequency of oscillation of the trolley is 2.0 Hz. I think that is an easy question. Compare this with A equals to negative omega squared x. So it means that omega squared is equal to 2k over m. Remember, omega is 2 pi f. So 2 pi f squared is equal to 2k over m. So it means we have that 2 pi f squared is going to be 2 times 64 divided by m. What was the mass? Where is the mass? The mass is 810 grams divided by 1000, that is 0.81. So I will divide, find the square root, and divide by 2 pi f. 2 times 64 divide by 0.81 square root, divide by 2 pi. So this is giving me F as 2.0 hertz. You can also verify. The maximum displacement of the troll is 1.6 centimeters. Calculate the maximum speed of the troll. Of course, we know that maximum speed V naught is omega times maximum displacement x naught. Remember, omega is 2 pi f, so times x naught. So this is 2 pi times f. F we have got 2.0 times x naught, which is 1.6 times 10 power negative 2. You check your calculator. So from the calculator, this is 0.20 to two significant figures, 0.20. The mass of the trolley is increased. The initial displacement of the trolley remains unchanged. Suggest the change, if any, that occurs in the frequency and the maximum speed of oscillations of the trolley. The mass is increased, so the frequency, what happens to the frequency if the mass is increased? Note that omega squared is equal to k over m. When m is increased, omega is decreased. Remember, omega is 2 pi f. When omega decreases, f decreases. So the frequency decreased or reduced. Then how about the energy? Remember, the speed. Of course, speed is equal to omega times x naught. We have seen that omega decreases. Automatically, v also decreases. So this one is also decreased. Okay, so that one is easy. A mass hangs vertically from a fixed point by means of a spring, as shown in the diagram here. The mass is displaced vertically and then released. The subsequent oscillations of the mass are simple harmonic. And they have given us a graph for the variation with the time t of the length L of the spring shown here. So let's find the length for equilibrium. So this is 17 and this is 13. So 17 plus 13 divided by 2. That is 20. 30 divided by 2 is 15. So the equilibrium position is at 15. I'll draw a horizontal line through 15 to show equilibrium position. So this is the line, this is the position for equilibrium. Equilibrium is around 15. So all measurements are going to be measured from 15. Okay. Use the figure to state two values of t at which the mass is moving downwards with the maximum speed. Downwards with the maximum speed. Note that L, what is L? L is the length of between the fixed point and the mass. So it means L increases when the mass is moving downwards. L increases when the mass is moving downwards. And it decreases when the mass is moving upwards. So we want a value when state two values of time at which the mass is moving downwards. It must be moving downwards when L is increasing. So we can look at this portion of the graph where L is increasing and this portion of the graph where L is increasing. The other portions, L is decreasing. So here it is moving downwards, here it is moving downwards because L is increasing. Okay, now we look for the values of time. State the values of time at which the mass is moving downwards with the maximum speed. The maximum speed is when the body is moving, passing equilibrium. And it is passing equilibrium at this point here. So we look for that value of time. It is in the middle of this box. It is also passing equilibrium at this value here, which is in the middle of that box. So just look for those values of time. On the x-axis, each small square is 0.1 divided by 10, that is 0.01. So this one is 2.2122 and a half. So it's 0.22 and a half. Half of this, that is 5, 225. Then here, this is 0.52. This is 0.5152 and a half. So it is 5, 2 and a half. Okay. So we have time as 0.225 and 0.525. That is the most technical question here. I have showed you the region, the parts where the mass is moving downwards, because from the diagram, L increases when the mass is moving downwards. So when you look at the graph, when the L is increasing, it means the mass is moving downwards. When L is decreasing, it means the mass is moving up or in the opposite direction. Okay. Determine for these oscillations the angular frequency omega. So omega is 2 pi f or 2 pi over t. Omega is 2 pi divided by t. So we just look for period. So this will be 2 pi over the period t. So let's check out for the period from the graph. I'll use this position here, or you can use from t equals to 0 to t equals to 0.3. That is one cycle. Or from this point here, 0.15, and this point here, which I think is 0.45. The difference is 0.3. So the period is 0.3. So this will be equal to 2 pi divided by 0.3. I press my calculator. So this is giving me approximately 21. Check again. Approximately 21 or 20.9. Okay, show that the maximum speed of the mass is that. So we now know that maximum speed V naught is equal to omega times x naught. And omega is 20.9 or 21 times x naught, what is maximum amplitude from the graph. Remember, equilibrium is at 15, so 15 to 17, that is 2 centimeters. So this is going to be times 2 centimeters, which will be 2 times 10 power negative 2. I press my calculator to verify. 20.9 times 2. So this gives me 0.418, which gives me 0.42. Use data from the figure 4.2 and A part 3 to sketch on the axis of the figure the variation with displacement x from the equilibrium position of the velocity v of the mass. So note that the maximum velocity is 0.42. On the vertical, the scale is each small square is 0.1 divided by 5, which is 0.02. So this one is going to be 0.42, 0.42. Remember, for speed, when speed is maximum, when displacement is 0, speed is maximum. So we have this one and this one here. Maximum speed is 4.2. And when displacement is maximum, speed is 0. And remember, the maximum displacement is 2 centimeters. When displacement is maximum, speed is 0. So we have these 2 points. Displacement maximum, speed is 0. Speed maximum, displacement is 0. Or displacement is 0, speed is maximum. So this gives us now an oval-shaped graph. That is not oval. I know people will draw squares. Okay, so that is the oval shape. The defining equation of simple harmonic motion is given as that. State the significance of the minus sign in the equation. So we now know that the minus sign shows that A and X are in opposite directions. So that means A and X are in opposite direction. A trolley rests on a bench. Two identical stretched springs are attached to the trolley as shown here. The unstretched length of each spring is 12.0 centimeters. The spring constant of each spring is 8.0 newtons per meter. When the trolley is in equilibrium, the length of each spring is 18 centimeters. That's when it is in equilibrium. So this is the equilibrium extension. The trolley is displaced 4.8 centimeters to one side. That is beyond equilibrium. To one side and then released. Assume that the resistive forces on the trolley are negligible. Show that the resultant force is 0.77 newtons. So the resultant, the force F is equal to K times X according to Hooke's law. And then what is K? K is 8.0. K is 8.0 newtons per meter times X. Now X is where there is comet. When the trolley is in equilibrium, the length of each spring is 18 centimeters. When it is in equilibrium. Remember, when it is not stretched, each spring has 12 centimeters as its original length. When it is in equilibrium, the springs are 18 centimeters. So it means the original extension here is going to be 12 minus 18. So the original extension E is going to be 18 minus 12, which is 6 centimeters. That is equilibrium extension. But then the trolley is again displaced 4.8 centimeters to one side, then released. So that means now, if I consider the spring which has been compressed, the effective extension of this spring is going to be now 6 centimeters. minus 4.8 centimeters, which is going to be equal, this is times 10 power negative 2. So that is now the effective extension, or that is the extension which is given beyond the trolley is displaced 4.8 centimeters to one side and then released. So if it is displaced to one side and then released, it means the compression caused the other side is going to be 6 minus 4.8. So what is that force? So this is going to give us 6 minus 4.8 times 0. Actually, this is 6 times 10 power negative that. And then the resultant force. So this is for the other side of the compression. That is for the other side of the compression. What is that? 0.6. Sorry, 0.6 minus 0.048. That is 0. So this is giving me 8.0 times 0.012. That is for the other one which is compressed. For this one which is extended, of course, the extension is going to be 6 plus 4.8. That is 6 plus 4.8, which is 110.8. So the other one, why can't I use tension? T2. T2 is going to be 8 times 6 plus 4.8, which is times 10 power negative 2, which is 8.0 times 10.8 times 10 power negative 2. So we want the resultant, which is the difference. So the resultant is the difference, which is going to be this minus that, or the other way around. So it will be 8 times 10.8 exponent negative 2 minus 8x times 0.012. So this is going to be T2 minus T1, which is giving me 0.768, approximately 0.77. Yeah, so that is approximately 0.77. Calculate. The mass of the fuel is 250 grams. So here I just go the tensions. We have seen a similar question. The tension here is T1, the tension here is T2. If it is displaced that side by 4.8, the extension here will be E minus X. Here it will be E plus X. This is X. We have seen E is 6 centimeters. Calculate the maximum acceleration A of the trolley. So we know that if the resultant force F is M times A, then the acceleration is going to be F over M. And F is 0.77. Mass is 250 times 10 power negative 3. From my calculator, so this is 3.1. Use your answer in Roman 2 to determine the period t of the subsequent oscillations. We also know that acceleration is equal to negative omega squared x. That means omega is going to be the square root of a over x. We ignore the negative. So omega is going to be the square root of acceleration is 3.1 over x. Since x was 4.8? Yes. So this is going to be 4.8 times 10 power negative 2. That is omega. But remember, period is 2 pi divided by omega. And this value of omega is 3.1 divided by 4.8 exponent -2 square root. This is 8.04. So it means the period is going to be equal to 2 pi divided by 8.04. 2 pi divided by 8.04. So this is giving me 7 point, no, not 7 point, 0.78. 0.781 or 0.78 seconds. Lastly, for today, the experiment is repeated with an initial displacement of 2.4 centimeters. State and explain the effect, if any, this change has on the period of the oscillation of the trolley. The experiment is repeated with an initial displacement of 2.4. I want you to note that we had a displacement of 4.8 centimeters. And for displacement of 4.8 centimeters, we had an acceleration, we had a force of 0.77 newtons. So how about if we now have 2.4 centimeters? Note that 2.4 is half of 4.8. State and explain the effect, if any, this change has on the period of the oscillation. Going back upwards, when the displacement was 4.8 centimeters, the force was actually 0.77. The displacement is since it has been halved, and we know that displacement is directly proportional to the force is going to be halved. When the force is halved, the acceleration is also halved. When the acceleration is halved, we are seeing that actually omega is going to change. We see that omega is directly proportional to omega squared is directly proportional to A. So A is going to be reduced. So state and explain the effect, if any, this change has on the period of the oscillations of the trolley. Although the resultant force is halved, the displacement x is also halved. And if the displacement is halved, then it means actually we are going to have the same period of time. We are going to have the same value of t. So the resultant force is halved. Resultant force is halved and the distance is halved. So if the resultant force is halved, the acceleration is halved, but the distance is also halved. So it means this is halved, the other one is halved, so there is no effect on omega. So the resultant force is halved and the distance is also halved. I think halved, this is HA. So T remains the same. So the period remains the same. So if the initial displacement is halved, the distance x is halved. Because the force is halved, the acceleration is halved. So these two are halved. So there is no effect on omega. And since omega affects the period, so since there is no effect on omega, then it means the period remains the same. So I would like to stop here for this video, and I hope for any errors, I am not a machine, so for any errors you can always raise them and correct them where possible. Thank you. I hope it has been educational to you, and we meet in part 4.